Our modern world is built on a foundation of digital trust. Every time you send a message, make a purchase, or access your bank account, you are relying on a silent guardian. Encryption. This complex web of mathematical locks protects our most sensitive information, forming the bedrock of global commerce, communication, and security. Now, imagine a key capable of unlocking every single one of those locks, all at once. Imagine a computer so powerful it could break the world's strongest encryption in minutes. Your bank accounts, private messages, corporate strategies, and even government secrets all laid bare. This isn't science fiction, it's the approaching reality of quantum supremacy, a monumental technological leap that promises to solve some of humanity's greatest challenges, but also threatens to rewrite the rules of cybersecurity forever. This is not just a new type of computer, it's a new paradigm of computation. To truly grasp the scale of this revolution, we first need to understand the world of classical computers that we live in today. For decades, the digital age has been defined by a simple yet powerful concept. Today's computers, from your smartphone to the most advanced data centers, use bits. These are the fundamental atoms of information, tiny electronic switches that can only be in one of two states, a 0 or a 1, off or on. Every app you use, every website you visit, and every security system that protects you runs on billions of these simple binary decisions. Even the most powerful supercomputers, marvels of engineering, are bound by this rule. They process tasks sequentially, step by step, limited by this binary logic. To solve a complex problem, they must try each possible solution one after another, like trying every key on a keychain until one fits. For many of the world's most critical problems, this keychain is simply too large to ever get through. Quantum computers, however, work differently. They operate in the strange and counterintuitive world of quantum mechanics. Instead of bits, they use qubits, or quantum bits. Thanks to a principle of quantum physics called superposition, a qubit isn't limited to being just a 0 or a 1. It can exist in a combination of both states at the same time. Think of it not as a switch that is on or off, but as a dimmer dial that can be at any point in between, and all points at once, until you look at it. This single difference is profound. Superposition allows a quantum computer to explore a vast number of potential solutions simultaneously. Instead of trying one key at a time, it's as if it can try millions of keys all at once. The number of possibilities it can explore grows exponentially with each additional qubit. But superposition is only half the story. Another quantum property called entanglement makes these machines even more powerful. Albert Einstein famously called it spooky action at a distance. When two or more qubits become entangled, their fates are linked. They behave as a single, unified system. Measuring the state of one qubit instantly influences the state of the other, no matter how far apart they are. This interconnectedness creates an incredibly efficient and powerful system for computation. By combining superposition and entanglement, quantum computers can tackle complex problems with a level of parallelism that is simply impossible for any classical computer, now or ever. This brings us to the concept of quantum supremacy. It's a specific critical milestone. It refers to the moment when a quantum computer successfully performs a calculation that a classical computer, even the most powerful supercomputer on Earth, practically cannot complete in a reasonable time frame. In 2019, researchers announced they had reached this milestone. A quantum processor solved a highly specialized mathematical problem in just over 3 minutes. It was estimated that the same task would take the world's most advanced traditional supercomputer approximately 10,000 years to complete. While the problem itself had no immediate practical use, the achievement was monumental. It was the hello world moment for a new era of computing power, proving that quantum machines could, in fact, outperform their classical counterparts on their own terms. So, why is this a threat? Modern cybersecurity, the system that protects nearly all digital information, depends on encryption methods like RSA and elliptic curve cryptography. The security of these systems relies on the difficulty of certain mathematical problems, specifically factoring massive numbers into their prime components. For a classical computer, this is an impossibly time-consuming task. The larger the number, the longer it takes, to the point of being practically unbreakable. But this is exactly the type of problem that quantum computers are uniquely suited to solve. An algorithm developed in 1994, known as Shor's algorithm, is designed to run on a quantum computer and find prime factors with astonishing efficiency. A sufficiently powerful quantum machine running Shor's algorithm could potentially break the encryption that protects global communications, financial systems, and national security. This leads to a growing and immediate concern within the intelligence and security communities, a strategy known as harvest now, decrypt later. Adversaries, be they nation-states or sophisticated criminal organizations, can intercept and collect vast amounts of encrypted data today. This data is currently safe, protected by classical encryption, but they can store it, waiting for the day when quantum computers become powerful enough to decrypt it all. This means that sensitive government communications, corporate trade secrets, and personal information shared today could be exposed years from now. The threat isn't just in the future, the vulnerability exists right now. If, or when, large-scale quantum attacks become practical, the consequences could be catastrophic across every sector of society. Global financial markets could be thrown into chaos as banking systems are compromised. The privacy of personal medical records could be eliminated overnight. Secure military and diplomatic communications could be intercepted, undermining national security. And the critical infrastructure of our smart cities, from power grids to traffic control, could be disrupted or held hostage. The very concept of digital security as we know it would need a complete and urgent transformation. The good news? The world is not standing still. The race is on, not just to build a quantum computer, but to build defenses against one. Cryptographers and researchers worldwide are developing a new generation of defenses known as post-quantum cryptography, or PQC. These are new encryption methods designed from the ground up to be secure against attacks from both classical and quantum computers. Instead of relying on prime factorization, these new systems are based on different, more complex mathematical problems, like those found in lattice-based or hash-based cryptography, that are believed to remain difficult even for a powerful quantum computer to solve. They offer a clear path toward a secure digital future. However, the transition to this new, quantum-safe standard of security is a monumental undertaking. It won't happen overnight with a simple software update. Governments, corporations, and organizations of all sizes must begin the long process of identifying their vulnerabilities, upgrading their legacy systems, adopting new cryptographic standards, and fundamentally rethinking how their data is protected for the long term. In the near future, a robust cybersecurity strategy will be a hybrid one. It will combine the strength of new quantum-resistant encryption, the intelligence of AI-driven threat detection systems, and the rigorous principles of zero-trust architectures to create multiple layers of defense against the next generation of sophisticated threats. Quantum supremacy is far more than just a scientific achievement or a technical benchmark. It is a profound wake-up call for our entire digital civilization, the very same technology that holds the promise to revolutionize medicine by designing new drugs, combat climate change by creating new materials, and advance artificial intelligence beyond our wildest dreams, could also be used to dismantle the security systems we rely on every single day. The quantum age is no longer a distant theoretical possibility. It is coming. The real question is, will we be ready for it?